So this alcohol dehydration reaction, alcohol plus sulfuric acid, something like this, and we get alkenes. We know this is now a E1 process, so it involves a carbocation, and so as soon as we have carbocation, we have the potential for rearrangements. We saw this in a large portion last week when we were doing SN1 reactions. I actually just looked at the notes a little bit earlier today. We did some problem like this last week, so let's just characterize this quickly as SN1. And I just looked at the notes. I don't have them right in front of me. Had some problem like this. I think we heated it in methanol. And you should draw on what you think the product, this was in the notes, so you should have done it. But one of the products is obvious and immediate. You should just draw right here, and then I'm going to draw a less obvious one right here. So you draw what product you think happens from the SN1 reaction here. No mechanism, just the product. And then there's one rearranged product that was also possible. So the one that you should have drawn should look something like this. This is immediately, obviously, and expected, this type of substitution product. And this one here is unexpected, but it's the result of a carbocation rearrangement. In SN1, we make a carbocation to be secondary here, and we can clearly see that there's been some sort of carbocation shift or skeletal shift because this isn't where it should have been. We're going to go through 3 different types of rearrangements for E1 reactions. We'll visit alkyl shifts and hydride shifts again. And we're going to start out with this particular molecule. A little bit different than the one we were using before. Previously we were using T-butyl alcohol. This one's a little bit different. From this particular molecule, if we took H2SO4 and excluded the possibility of rearrangements, what are the major product or products you would anticipate from this? So not a mechanism problem now, but you could point it on finger or think about what's happening first. Well, water attacks acid, this gets protonated, it turns into a good leaving group, it leaves. We have a carbocation here, and then we have to explore all beta positions for hydrogens. Do that in your mind and draw on the product that you think belongs here. Again, when I'm leaving these little moments and intervals of 30 seconds, 60 seconds, it's very critical you actually draw something and do something, and not just sit there and wait. Best students right now are drawing things furiously, thinking, and people who are actually drawing things, even if it's wrong, actually get the most benefit from this. If you just wait, you're not getting what the intended purpose of why I'm putting this pause here. So what product would you anticipate from what we've studied today in our preview lecture for E1 reactions? Make a carbocation where the alcohol was, because the alcohol gets protonated, leaves. There's only one beta position with hydrogens, it's this one. And if we did an elimination at that position, this is the alkene I was hoping some of you would draw. Right between here and here, we can have an elimination. If this is carbocation, there's no hydrogens attached to this carbon, but there are to here. Conjugate base pulled in, pluck this off, we can make a double bond here. So even though I'm not drawing a mechanism, I can easily just think like, oh, this is the carbocation, here's the hydrogens, this is where the double bond would be. Or maybe some of you sketched out the mechanism, that's fine. Sadly for us, the person who ran this reaction, they had their heart broken. They were trying to make this, and at the end of the day, they only got 3% of this. The major components they got were this one, and this one. So carefully draw these two alkenes in to your notes. Carefully draw these two alkenes into your notes. Turned out this was isolated in 64% yield and 33% yield. These are very, very unexpected. For me, this one here, perfectly expected. When this reaction was run, these things occurred, and our preview lecture should have prepared us a little bit for this problem. Rearrangements are possible, and if I were to draw this particular problem on the board or problem on an exam, I would give you these two particular products and say give a detailed reaction mechanism that explains the formation of these products. As you start it, you would readily predict this alkene. Then at some point you'd say, well, I don't know how to make this or this from the starting carbocation. So let's just draw the carbocation directly. We don't need to practice. You can practice on your own making this carbocation. It's actually not difficult. But this is the carbocation that led to this particular product. And on your own, do the mechanism. This reacts with that. I'm definitely going to ask you mechanisms about this. So you have to practice it. And we can readily see, if we look at this alpha, beta, beta, well, there's only one beta position that has hydrogens. That leads to here. But this does not lead to either of these two things. And there's some striking problems we can see with this. I see a T-butyl group in this molecule and an ethyl group. On the left molecule, I see T-butyl and I see ethyl. On any of these, I don't see any T-butyls. In fact, I see something that's kind of like isopropyl and propyl, isopropyl, or 3 carbons, but I don't see any carbon attached to 4 carbons. There's a carbon here attached to 4 carbons. There's a carbon here attached to 4 carbons. Nope. Nope. So something is rearranged, something is moved, and the way that we always approach rearrangements is we take this carbocation, we label things alpha and beta, and we explore different possibilities. So what we're going to do now, we've explained this product just by doing an elimination reaction here. We're going to redraw this, and we're going to look for carbocation rearrangements. There has to be one that helps us explain those products that we just formed. We call this alpha, and we call all carbons, all unique carbons, beta at this point when we're looking for rearrangements. So we're looking for rearrangements now. The way that we always did this before, we took our carbocation, and we looked at all beta positions, and we're going to expand those beta positions and see what we have. Some of you should already predict or anticipate what you know about carbocations. Which one is going to be more fruitful? If we move a group, should we move something from the beta 1 position to here, or should we move something from the beta 2 position to here? One of those two is going to be more fruitful than the other, but we're going to explore both. At beta 1, we simply expand. So what I've done here is I've expanded the beta 1 position. The only thing we have here are hydrides. They're all identical. Let's move one. Let's do a 1-2 hydride shift. When we do that, we can redraw the carbocation. Many of you already know this is folly. Many of you already can see this is making something very unstable. If that's not you, well, now, once we actually draw it, we can compare these two, and energetically, we're making something worse here. So this product just simply will not happen. Even energetically, it's impossible, and if we look at this very carefully, this is not going to help us explain those two products, right? If we made this carbocation, made a double bond here, this doesn't help us explain those two unexpected products. So this doesn't work. And maybe some of you were already more tuned into the fact that at the other position, we had methyl groups. And so this is the beta 2 position. It's already expanded. We have 3 identical methyl groups. Doesn't matter which one we pick. We're going to do an alkyl shift or a methyl shift. We do so by taking this pair of electrons and this whole group, we move it over. This will be called a 1,2 alkyl shift, or this one specifically, since it's a methyl group, it's a 1,2 methyl shift. When we move it, the skeleton is rearranged. This will happen spontaneously if we can make something better than where we started. We have to be really careful about what we actually draw here. We have to make sure that we have all the carbons that don't move in place, all the hydrogens that don't move in place, and if we break a bond and make a bond, which is this one right here, then the carbocation is going to go to where that bond originally was, and we see crystal clear here that this is a tertiary carbocation. This is a great choice for us to explore and think about. It's more stable than where we started from. And if we take this carbocation now, that's more stable, rearranged. We take this carbocation, can we actually explain those 2 other products that we had? So we have now our rearranged carbocation. Here's its alpha position. We're going to relabel this alpha. And if we're looking for E1 reactions now, we've got a new carbocation. It's more stable than where we started from a methyl shift. If we're going to do an E1 reaction, we again put our attention on the carbocation, and we have to look for hydrogens at beta positions. Here's one at beta 1, and here's some at beta 2. I'm not going to do these individual steps here and mechanisms. I'm not going to write it all out. But what I want you to do right now, we're going to draw 2 boxes here. I know you have your notes open, right? From the previous page, we could look at it. But what I want us to do is I want you to draw the product that you would expect from beta 2 elimination here and from beta 1, right? If we just pluck off a proton at beta 2, what does our alkene look like? If we pluck off this 1 proton at beta 1, what does the alkene look like? Try not to look at the notes that are sitting right in front of you because the answer's there. But instead, I'd really rather you just try and draw alkenes here and here by these clues that I'm leaving you, okay? Identify these 2. And you could do the mechanism, but that's going to take a couple minutes. What I'd rather you do is try to anticipate what product is going to form from pulling off this acidic proton at this 1 carbon removed from our new carbocation. What's the alkene going to look like if we pull off a proton from this beta 2 position? All right, this other 1 carbon removed position. Beta 2, if I pull off a proton, we should have a double bond here. Rest of the molecule stays the same. So something like this. Maybe you have an extra hydrogen drawn in, or maybe you drew off carbon here, hydrogens, but there's lots of ways to represent these molecules. The other one we could have, we pulled off that other hydrogen at beta 1. We make this particular alkene. Then we can just check our work. Does this work match the unexpected products on the previous page? And it absolutely does. So we're going to use carbocation rearrangements on our 3rd exam. You're going to use them to explain otherwise unpredicted products, things that we wouldn't naturally predict for this reaction. I'm going to remove this right now. I'm going to leave it up here just for about 10-15 seconds. If you need it back, just let me know. But I just want to go back to 2 pages in the notes, 1 page in the notes where I first put this problem up. So again, you can on your own practice the full-blown mechanism to explain these things. Just very quickly looking at these, you should be able to anticipate the types of products that would form. So again, if we see a problem like this on an exam and I say predict the product of it, you should predict this. This is what I expect from everyone in the room, that this would be the sole product you would predict from this reaction. When a carbocation rearrangement is something that I want you to explore, I'll be drawing something like this. Or maybe something like this. Maybe I'll cover up that there. And instead I would draw the whole reaction here with these products and say something like the following. Give a detailed reaction mechanism that explains the experimental outcome of this reaction. Give a detailed reaction mechanism that explains the formation of these two products. As you start through this, you'll quickly realize that this is what you should form, and the only way to explain this would be through carbocation rearrangement. So this is not going to be 80% of the test, 90% of the test, 95% of the test. If you look back in the totality of our notes, we've spent less than an hour on carbocation rearrangements out of some 12, 14, 15 hours of our time together. We should be able to do the math on that and determine how important this is or how much you think it might be on the exam. But I wouldn't anticipate a huge portion of it. Just